Hi everyone. In this video, we're going to discuss L'Hopital's rule. Now, L'Hopital's rule is a means by which we can evaluate limits that take an indeterminate form like 0 divided by 0 or infinity over infinity. And there are other indeterminate forms that we'll consider in a few minutes. Now, the reason we call these indeterminate forms is because we cannot consistently assign a value to them. You may think that 0 over 0, couldn't we assign a value of 1 to that because it looks like 3 divided by 3? Well, no, you can't do that, and we'll see why in a second down here. And the same thing with infinity over infinity. You can't assign a value to that like 1. Now, to see why we can't assign a value to 0 divided by 0, consider these two limits here. The first one, we have the limit as x approaches 1 of x squared minus 1 divided by x minus 1. Now notice that is of the form 0 over 0, because if we put 1 in for x in the numerator and denominator, we get 0 over 0, so it is of this form. Now if we evaluate this limit, what we get is, you see how we can cancel the x minus 1 terms when we expand the numerator, and you get 2. Okay, so the first limit here is of the form 0 over 0, and we get back to number 2. Now if we evaluate this limit down here, we just changed it a little bit, so we now have the limit as x approaches 2 of x squared minus 4 over x minus 2. Notice this is also of the form 0 over 0, because if we put 2 in for x, we get 0 in the numerator and 0 in the denominator. Now if we expand the numerator as x minus 2 times x plus 2, you see how these x minus 2's will cancel, and we get our limit equaling 4. So you see we have two limits here, both of the form 0 over 0, yet they yield different numbers. And so you see we can't consistently assign a value to 0 over 0. The only way we could assign a consistent value to that is if every limit of the form 0 over 0 were equal to a specific number. Then we could assign a value to this. But that doesn't happen. In fact, you could create limits that are of the form 0 over 0 that approach any number you want. So there's no way we can consistently assign a value to this. And the same thing is true for infinity over infinity. We can construct limits that are of the form infinity over infinity that take on any number you would like. Now in this lesson, we're going to study several different types of indeterminate forms split into two classes. Now the first type of forms that we study are going to be 0 over 0, infinity over infinity, 0 times infinity, and infinity minus infinity. So these four indeterminate forms, when we run across them, we will tackle them in a similar manner. And these are all indeterminate forms. We'll justify a few of them later on. Now the other type of indeterminate forms are 1 to the infinity power, 0 to the 0 power, and infinity to the 0 power. When you run across limits like these, they are also indeterminate forms, and we'll have a different way of tackling those limits as compared to the first four. So these are the 7 types of indeterminate forms that we have, and we'll study how we can evaluate each of them. Now let's take note of something important. If you start with the form as 0 divided by 0, you can show that all the other forms, infinity over infinity, 0 times infinity, and so on. So when you have limits that look like these, indeterminate forms, you can actually rewrite them so that they turn into this form. So in other words, all these forms are actually equivalent to 0 over 0. So that's why all of these are indeterminate, because 0 over 0 is indeterminate, and you can show that if you have a limit like infinity over infinity, you can rewrite it so it takes on the form 0 over 0, and since 0 over 0 is indeterminate, so is infinity over infinity. For example, to see why, consider this. Suppose we have a limit of two functions, limit as x approaches c of f of x divided by g of x, where f of x is approaching infinity and g of x is approaching infinity as x approaches c. So this would be of the form infinity over infinity. So suppose that we have that. Now, if you simply take this limit and you rewrite it like this, so you notice we took f over g and simply rewrote it as 1 over g divided by 1 over f, right? That's the same thing. Algebraically, this is the same as this, right? If I just multiply top and bottom by f, we recover the left-hand side, okay? Now, if f is going to infinity and g is going to infinity, then that means 1 divided by g is actually going to 0, and 1 divided by f is going to 0, right? Because 1 divided by a really large number is a really small number, a number close to 0. And the same thing for the denominator. So you see what we just did is we took a limit of the form infinity over infinity and just algebraically rewrote it as a limit of the form 0 over 0. So therefore, since 0 over 0 is indeterminate, we can't assign a value to it. Neither can we assign a value to infinity over infinity because it is the same algebraically as 0 over 0. And so that's why these two forms are equivalent. And the same thing holds for all the other ones. You can show that all these other forms are equivalent to 0 over 0 by rewriting them. Now let's take a look at the statement of L'Hopital's rule, then we'll look at a few examples, and then we'll take a look at the proof of L'Hopital's rule eventually. Now here's a statement for L'Hopital's rule for the case 0 over 0 or infinity over infinity. So if we have two functions f and g, and we assume that they are differentiable on an open interval, a, b, containing some point c, so c is in between a and b, and we also need to assume that the derivative of g does not equal 0. Okay, we do need to assume that for x in the interval a, b, except possibly at c. It doesn't matter what happens at the c value. Then, if the limit as x approaches c of f divided by g results in the indeterminate form 0 over 0, or plus and minus infinity over plus and minus infinity, then the limit as x approaches c of f divided by g is equal to the limit as x approaches c of the derivative of f divided by the derivative of g, provided that the limit on the right-hand side does exist. Now notice just one thing in the discussion of this theorem before we look at some examples. You notice how we're using indeterminate forms plus minus infinity over plus or minus infinity. Before we just stated infinity over infinity. Well, if this is an indeterminate form, then so is negative infinity over infinity, or infinity over negative infinity, and all the combinations thereof. You know, negative infinity over negative infinity is also an indeterminate form. So just for brevity, we only write infinity over infinity like this, but this covers all of the other cases, so here we stated it as plus minus infinity divided by plus or minus infinity. But all of these are also indeterminate forms. And the same thing for 0 times infinity. It doesn't matter if this is a plus or minus infinity 0 times negative infinity would still be an indeterminate form. Now there's one other thing to note here before we look at some examples. L'Hopital's rule can also be applied to left and right hand limits like this, like these two, limit as x approaches c from the right or c from the left. You can also apply L'Hopital's rule to left and right hand limits. You can also apply L'Hopital's rule to limits when the c is plus or minus infinity. So you can apply L'Hopital's rule to situations like this, limit as x approaches infinity of f over g, or limit as x approaches negative infinity of f divided by g, as long as the limit is of the form 0 over 0 or infinity over infinity. Now let's take a look at an example where we apply L'Hopital's rule. So down here we have a limit that you've all seen from Calculus 1. The limit as x approaches 0 of sine x over x. That was a very important limit in Calculus 1 because we used it when we evaluated the derivatives of the trigonometric functions like sine and cosine. So this is a very important limit. And you'll recall that this limit is 1. Okay, let's prove that using L'Hopital's rule. Now, if you recall from Calculus 1, you may have proven this theorem using a very laborious technique using inscribed triangles and sectors, and it was a very difficult proof to go through. L'Hopital's rule makes this result very easy. So all we have to do is this. First of all, notice that if I put 0 in for the x in the numerator and the denominator, the sign of 0 is 0. And of course I get 0 in the bottom. So this is of the form 0 over 0. It has to be of this form, or infinity over infinity, in order to apply L'Hopital's rule. If it isn't of one of these forms, you can't apply L'Hopital's rule. Alright, so it is definitely of this form. So now what we have to do is just take the derivative of the top, derivative of the bottom, and see if we get a limit. So that's exactly what we're doing right down here. So you notice we evaluate the limit as x approaches 0 of the derivative of the numerator divided by derivative of the denominator, right? See, that's the f prime over g prime part right here. And derivative of sine is cosine. Derivative of x is just 1, of course. Now, this limit does exist, right? You can plug 0 in for x and it works out perfectly well. Putting 0 in for x here, the cosine of 0 is 1. The denominator here, there's no place to put a 0 in, so its limit is just 1 as well. 1 over 1, of course, is 1. And there you go. We have just proven the result from Calculus 1 that this limit is 1 using L'Hopital's rule. Okay. So that makes it very easy. Now, of course, you have to keep in mind we still have to prove L'Hopital's rule, and the proof of that is a little challenging. But once we have this rule, it allows us to evaluate many different types of limits instead of trying to tackle each limit of this form individually to try to figure out what its value is. Let's take a look at a few more examples. Now here we have an example of a limit that is of the form infinity over infinity. So here we want to evaluate the limit as x approaches infinity of the natural log of x divided by x. So the first thing we need to do is make sure that this limit is of the form 0 over 0 or infinity over infinity in order to apply L'Hopital's rule. So you notice as x goes to infinity, the numerator, the natural log of x, that does approach infinity. And as x goes to infinity, of course, x approaches infinity. So this limit is of the form infinity over infinity. So we are justified in applying L'Hopital's rule. So to apply L'Hopital's rule, we just need to take the derivative of the numerator divided by the derivative of the denominator and see if that limit exists. And that's what we're doing right here. So you notice at this step right here, we took the derivative of the numerator divided by the derivative of the denominator. Now the derivative of ln x is 1 over x. Derivative of x is 1. And now we take this, simplify it, and see if the limit exists. Well, of course, this simplifies as the limit as x approaches infinity of 1 over x, and that is 0, right? As x is approaching infinity, 1 over x is going to be approaching 0. And since the limit of this quantity right here is equal to 0, you are justified in saying that the original limit we started with is equal to 0 as well. Now let's take a look at an example where we have to apply L'Hopital's rule multiple times to get an answer. Now here we want to evaluate the limit as x approaches pi over 2 of the quantity 1 minus sine of x divided by 1 plus cosine of 2x. Now first of all, let's see if we even need to apply L'Hopital's rule. Well, if we put the pi over 2 in for the x into the numerator and denominator, notice that we get 1 minus the sine of pi over 2, that's what we have right here. Now the sine of pi over 2 is 1, so we get 1 minus 1 in the numerator. And if we put pi over 2 into the denominator for x, we get 1 plus the cosine of pi. The cosine of pi is negative 1, so we get 1 minus 1, and yes, we get 0 over 0. So this limit is of the form 0 over 0, so we can apply L'Hopital's rule. So applying L'Hopital's rule, we just take the derivative of the numerator divided by the derivative of the denominator, so that's what we're doing right here. So the derivative of 1 minus sine x, that is negative cosine x, right? Derivative of 1 is 0, derivative of sine is cosine, so we get negative cosine right here. Then the derivative of the denominator is going to be negative 2 times the sine of 2x, right? Just have to use a little chain rule here. Derivative of cosine 2x is negative sine of 2x times 2, right? Little chain rule there. So the derivative of the denominator is negative 2 times the sine of 2x. Now if we put pi over 2 in for x in the numerator and the denominator, notice that we get negative the cosine of pi over 2 divided by negative 2 sine of pi, right? 2 times pi over 2 is going to be pi. Well, the cosine of pi over 2 is 0, and the sine of pi is 0, so we are still of the form 0 over 0. So that means we can apply L'Hopital's rule again. Now also notice right here, before we apply L'Hopital's rule again here, we cancel these negatives, right? So we get this limit right here, and this is of the form 0 over 0 again, as we just discussed. Now we apply L'Hopital's rule again to this. So down here we take the derivative of the top, divide by the derivative of the bottom, that's what we have right here. And then the derivative of cosine is negative sine. Derivative of sine of 2x is 2 times the cosine of 2x, so, and we have this 2 hanging around, so that turns into a 4, and we end up with this limit. And let's just scroll down here a little further. Now we have to evaluate this limit right here. Well, you notice we don't have any trouble evaluating it now. If we put pi over 2 in for the x in the numerator, the sine of pi over 2 is 1, so we get negative 1 in the numerator. So this is going to be right here, negative 1. Sine of pi over 2 is 1. And if we put pi over 2 into the denominator, for x, we get the cosine of pi. Cosine of pi is -1, so 4 times -1, we get -4. And we finally get a limit 1/4. And so there you go. So therefore what we can say is, going back to the original limit that we have all the way up here, this limit is 1/4. And so you see what we had to do is apply L'Hopital's rule 2 times. Now let's take a look at a few more examples, but before we do that, we need this rule. So this rule states that when you're applying L'Hopital's rule to limits of the form 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, or infinity to the 0, then you must algebraically convert them into a limit of the form 0 over 0, or infinity over infinity first, and then you can apply L'Hopital's rule. Now let's take a look at this example. So here we want to evaluate the limit as x approaches 0 from the right of x times the natural log of x. Now let's notice what form this limit is. So as x is approaching 0 from the right, the x is approaching 0. And if you think back to the graph of the natural log, remember the graph of the natural logarithm looks like this. So as x approaches 0 from the right-hand side, you'll notice that the natural logarithm goes down to -infinity. So the natural log of x is approaching -infinity. So this limit is of the form 0 times infinity. All right, so to apply L'Hopital's rule, we must convert it into the form 0 over 0, or infinity over infinity. So to convert it into one of these forms, let's do this. So here we have our limit. Let's rewrite x times the natural log of x. Let's rewrite that as ln x divided by 1 over x. So you notice these are the same thing, right? If we just take that denominator and flip it up, we recover the left-hand side. Now as x is approaching 0 from the right, the ln of x is approaching -infinity. And as x is approaching 0 from the right, 1 over x is approaching infinity, right? If I take 1 divided by a very, very small positive number, that's going to be a very large positive number. So this limit, which is the same as this one, as x is approaching 0 from the right, will be of the form -infinity over infinity. So it's going to be an infinity over infinity, and we can apply L'Hopital's rule to this right here. Now you notice in the process of doing this, what we've just done is we've verified that a limit of the form 0 times infinity is equivalent to a limit of the form infinity over infinity. Okay, so that's why this is an indeterminate form, because we can turn it into a limit that looks like either infinity over infinity, or we could have done 0 over 0 as well in this problem. Now what we have to do is evaluate this. Okay, so applying L'Hopital's rule, we take the derivative of the numerator. That's going to be 1 over x. Derivative of the denominator is -1 over x squared, right? Derivative of 1 over x, right? That is -1 over x squared, recall. All right, think of this as x to the -1 power. Now, simplifying this right here, this simplifies as -x, and we get 0 for our limit then. Right, limit as x approaches 0 from the right of -x is just 0. And so that is our answer. So there you go. So this is equal to 0. And once again, we did that by writing x times ln x as ln x divided by 1 over x. This is of the form infinity over infinity, and we applied L'Hopital's rule. Now notice one other thing here. We could have taken this limit and we could have written x times ln x like this as well. We could have written it as x over 1 over the ln of x like that. In which case this limit would have been of the form 0 over 0. And you could apply L'Hopital's rule to this as well, and you'll still get an answer of 0. However, the reason we chose to do it like this is because it's a little easier. It's a little easier to differentiate 1 over x than 1 over the ln of x, although it would still work out just fine if you had written it like this. Now let's take a look at the indeterminate forms 1 to the infinity power, 0 to the 0, and infinity to the 0. Now these three forms are in fact indeterminate forms, because when you encounter limits of these forms, you can show through some algebraic manipulation that you can change your limit into a limit that has the form 0 over 0 or infinity over infinity. And since these are indeterminate forms, these will be also. Now in this discussion right here, we show that you can rewrite a limit of the form 1 to the infinity as a limit incorporating the form 0 over 0, and since that is indeterminate, so is 1 to the infinity. Now, I'm not going to go over this in detail. What I want to do is take a look at an example that shows you how this works. So we're going to take a look at an example of a limit that is of the form 1 to the infinity power, and then show you how to turn it into a limit that incorporates 0 over 0 in it, and then apply L'Hopital's rule to this. So let's take a look at this example. Now here in this example, we want to evaluate the limit as x approaches infinity of 1 plus 1 over x to the x power. Now let's note what form this limit takes. As x is approaching infinity, 1 plus 1 over x is going to be approaching 1, right? Because the 1 over x term right here, that is going to be going to 0. Okay, so the base here of our exponent is going to be approaching 1. And of course the exponent, as x approaches infinity, the exponent is going to be approaching infinity. And so this limit is of the form 1 to the infinity power. Now let's see how we can evaluate this. So what we're going to do is algebraically manipulate it and show that a limit of the form 0 over 0 comes out. So here's how we do that right here. So notice that we can write this limit, the limit of this quantity, as e to the x times ln 1 plus 1 over x power. Now to see how we get this right here, just take note that e to the natural log of any value is x, right? Okay, so recall that. So what that means is we can write this quantity right here as and so there you go. So you see how we can write this as e raised to the x times ln of 1 plus 1 over x, just using properties of exponentials and natural logarithms, right? Recall how we can drop this x in front of the ln by properties of the natural logarithm. So you see how this is equal to this quantity right here. And now what we can do is just move the limit into the exponent. Okay, the e is a fixed number, it does not change as x varies to infinity. So we can just realize that this quantity is e raised to the limit as x approaches infinity of x times the ln of 1 plus 1 over x. Now if we consider the limit in the exponent, notice that this is an indeterminate form, because as x approaches infinity, this x is approaching infinity. And as x approaches infinity, the ln of 1 plus 1 over x, that's approaching the natural log of 1, but the natural log of 1 is 0. So we see that the natural log term is approaching 0. So you see we have a limit of the form infinity times 0, which we know is an indeterminate form from the previous discussion. So now let's see how we can evaluate this as we did before by rewriting it as a limit of the form 0 over 0 or infinity over infinity. So here we have the limit of the exponent. So we will write this as the limit as x approaches infinity of the natural log 1 plus 1 over x divided by 1 over x. Notice that this is the same as what we have right over here. Okay, if we just flip that 1 over x back up into the numerator, we would recover this. Now we see that this is of the form 0 over 0, right? As x is approaching infinity, the natural log of 1 plus 1 over x is approaching the natural log of 1, which is 0. And as x approaches infinity, 1 over x is approaching 0 as well. So we are of the form 0 over 0, so we can apply L'Hopital's rule. Now, differentiating the numerator and the denominator, this is what we get right here. Just notice that the derivative of the numerator here, if we were to differentiate this, I'll just show you right here, d dx that, you will get 1 over 1 plus 1 over x times the derivative of 1 over x, which is negative 1 over x squared. So that's what we have right here. And then the derivative of the denominator is negative 1 over x squared. So there you go. So derivative of the top over derivative of the bottom. Now, we can see that the 1 over x squares cancel. This negative will cancel with that negative. And we end up with this limit right here. Now as x approaches infinity, 1 over 1 plus 1 over x, well, this term is going to 0. And we got our answer of 1. Okay, now that was the limit of the exponent term up here. Okay, so that was of the form infinity times 0. We rewrote it as a 0 over 0 form. Applied L'Hopital's rule, we came up with an answer of 1. So that means that the original problem, this limit right here, is going to equal e to the 1 power. We determined that this limit right here is 1. So our answer down here we see is e to the first power, or e. So that's what this quantity is approaching. And this also shows you why 1 to the infinity is an indeterminate form, because we rewrote it as a limit of the form 0 times infinity, which is already indeterminate, we know that. And also to evaluate this, we rewrote it as a form 0 over 0. So that shows you why 1 to the infinity is an indeterminate form. Now let's take a look at this result. Now this limit that we just evaluated right here, we found that this was equal to e to the 1 power. This limit can be generalized as follows, and this is a pretty important limit. So right here is the statement that, in general, the limit as x approaches infinity of 1 plus r over x to the x power is equal to e to the r power. So for example, if you looked at the limit as x approaches infinity of 1 plus 2 over x to the x power, you'll see that that is equal to e squared. Okay, so this value that's right here, this limit is going to equal e to that value. Now if you look back at the previous example, you'll see how you can easily manipulate that example to prove this result. For example, let's just take a look at that. All you would have to do in this example here is change this number 1 right here to an r. These would become r's right in here. This would be an r right there. You would have an r right there. Then when you differentiate the numerator, what you're going to get is this quantity times r over x squared, right? The derivative of r over x is negative r over x squared. And so then you're going to get an r right there. And you'll see this limit is r. Then you go back to your original problem and you see that your answer is e to the r power, right? This piece right in here is arguing that the limit in the exponent right here is actually r. And there you go. So you can go back and just change that 1 right there that's in the numerator of the 1 over x term, change it into an r, follow this argument down, and you'll see that you get e to the r power. Now in this example, we're going to take a look at a limit that is of the form 0 to the 0 power. So here we want to evaluate the limit as x approaches 0 from the right of x to the x power. Now you notice that since x is approaching 0, this is of the form 0 to the 0 power, right? Now in a manner similar to the previous examples that were of the form 1 to the infinity power, we're going to use exponentials and logarithms to manipulate this limit and show that we get an indeterminate form of the form 0 times infinity. And then we'll be able to evaluate that limit by rewriting it either as 0 over 0 or infinity over infinity. So here we want to manipulate the term x to the x power. So notice that we can rewrite it as e to the ln of x to the x. Drop the exponent down in front of the ln and we get this result. So therefore we have x to the x equals e to the x times ln of x. And so looking back at our limit, we see that we can move the limit into the exponent and write it like this. Now what we need to do is evaluate the limit that's in the exponent up here. Now you'll notice that this is of the form 0 times infinity, right? So that exponent, I'll just put it right here, that is. So you notice as x is approaching 0 from the right, this is going to 0, of course. This is going to negative infinity. And so this limit is of the form 0 times infinity, which we know is an indeterminate form. And now this also shows us why 0 to the 0 power should be considered an indeterminate form, because we have shown algebraically that when we manipulate it, we get out a limit of the form 0 times infinity, which is also indeterminate. Now we need to evaluate this limit, so we need to put this limit here in the form either 0 over 0 or infinity over infinity and apply L'Hopital's rule. So here's how we do that. So right here we have the limit of the exponent. Now we're going to write x times ln x as ln x divided by 1 over x. All right, you see that if I flip this 1 over x back into the numerator, we do recover this. Okay, now you see this is of the form infinity over infinity, because as x is approaching 0 from the right, ln of x is approaching negative infinity, and 1 over x is approaching infinity. So you see this limit is of the form infinity over infinity, so we can apply L'Hopital's rule. So now applying L'Hopital's rule, the derivative of the numerator is 1 over x. Right, there it is. The derivative of the denominator is negative 1 over x squared. Right, there it is. And then just simplifying this, of course, just flip the 1 over x squared into the numerator, and you get the limit as x approaches 0 from the right of negative x, which is 0. Okay, so that's the limit of the exponent up here. And so we see that the limit of x to the x power as x approaches 0 from the right is e to the 0, which is 1. And there you go. That's our answer. Okay. And keep in mind in this discussion, we also verified why 0 to the 0 power should be considered an indeterminate form, because you can algebraically manipulate it into a form that incorporates the indeterminate form 0 times infinity. And now let's consider one important result: exponential versus polynomial growth rates. So here we want to argue that the limit as x approaches infinity of x to the n power divided by e to the x is 0 for any integer value n. Now this is actually an important result. So it shows us that if we consider the limit as x approaches infinity of x to any power as large as you want, say 1,000 power, x to the 1,000th power, that's a really fast-growing polynomial, divided by e to the x, this limit is 0. So this shows us that the exponential in the denominator grows much faster than the polynomial in the numerator does. Because the limit is 0, the bottom has to be going to infinity much, much faster than the numerator is going to infinity. Okay, so that's what this result is stating. And it doesn't matter what you put in the exponent here. You know, you could put 1,000,000 up in here. X to the 1,000,000th power. The exponential still grows faster than x to the 1,000,000th power does as x goes to infinity. This is an important result. Now we can easily prove this with L'Hopital's rule. So consider this. We start out with the limit as x approaches infinity, x to the n over e to the x for any integer n. Now if we apply L'Hopital's rule, notice that we can apply L'Hopital's rule first because of course this is of the form infinity over infinity, right? As x is approaching infinity, both numerator and denominator are going to infinity. So if we apply L'Hopital's rule one time, we get this result. Notice the derivative of x to the n is n x to the n minus 1. Derivative of e to the x is e to the x. Now this is still of the form infinity over infinity, right? So we can apply L'Hopital's rule again. And here we did it again. So notice we drop the n minus 1 down, so we get n times n minus 1, x to the n minus 2 power, and then in the denominator we still have e to the x. Now this, as long as the exponent is still non-zero, this is still of the form infinity over infinity. And so you see we can keep applying L'Hopital's rule until eventually we have this exponent knocked down to x to the 0 power, or just 1 right here. And then finally in the numerator we have a single number divided by e to the x, right? And now this limit is certainly 0, right? Notice in the numerator, more specifically, we get n factorial after we differentiate the x to the n, n times, we end up with n factorial, which is a number divided by e to the x. This is going to infinity, and so our answer is 0. So that proves that this limit up here is indeed 0. Okay, just notice one thing here, for example, where that n factorial is coming from. For example, if I differentiate x cubed 3 times, we get right? Notice this is the first derivative, second derivative, third derivative, and notice that this is 3 factorial. So that's where that n factorial is coming from. Okay, so that proves that the exponential function e to the x power grows faster than any polynomial of any degree. That's actually a very important result. Now, down here we have another result which generalizes this a little bit. For any constant a greater than 1 and any other constant n, the limit as x approaches infinity of x to the n divided by a to the x is 0. So just to put that up here, so what this is saying, as long as the base of your exponential function is greater than 1, that a has to be bigger than 1, this exponential will grow faster than x to any power n. No matter what value you put in for this n, as large as you want, the exponential function here will still grow faster than x to the nth power. And this can also be proven using L'Hopital's rule. Just note that if you were to apply L'Hopital's rule n times, eventually the numerator here would become n factorial again. And each time you differentiate the denominator here, just take note that the first derivative of the denominator is going to be the natural log of a times a to the x. That would be the first derivative. Then the second derivative would be the natural log of a times the natural log of a again, times a to the x. So each time you differentiate this, you're going to pick up another natural log of a term. So after differentiating this n times, eventually you're going to get the natural log of a to the nth power times a to the x. So after applying L'Hopital's rule to this n times, you would eventually get that. And of course this is 0 because what's in the numerator is a constant. This term will be going to infinity. And there you go. Okay. So once again, take note that this shows that if we consider a polynomial like x to the 1000th power divided by, say, 1.1 to the x power, this function down here, 1.1 to the x power, grows faster than this polynomial. No matter how large the exponent is in this polynomial, the exponential function 1.1 to the x power still grows faster than this polynomial. And that concludes this discussion about how to use L'Hopital's rule.